Hi everyone. Today I want to talk about one aspect of statistic, which is hypothesis testing. Do you ever wonder why we need hypothesis testing? Imagine you're a scientist and you just develop a new fertilizer and you just want to know if it makes plants grow taller than usual. You measure sample of plants and yes, they look a little taller, but here's a problem. How do you know if that difference is real or if it's just a random chance? That's where hypothesis testing comes in. It's a structured way to decide whether the evidence from your sample is strong enough to make a claim about the entire population. In other words, it helps us separate signal from noises. First of all, we need to understand the language of hypothesis testing because every hypothesis test follows the same basic steps. So let's walk through them. Step 1. State the hypothesis. The null hypothesis, which is H0, is nothing is happening statement. For our fertilizer, H0 says the fertilizer has no effect on plant height. The alternative hypothesis, which is H1, stands for something is happening statement. For our fertilizer, H1 says the fertilizer increases plant height. Step number 2, choose a significance level alpha. What actually is significance level? It represents the maximum probability of making a type 1 error, that is, rejecting the null hypothesis H0 when it is actually true. The most common choice is 0.05 or 5%. That means we're willing to be ground 5% of the time if we reject H0. In high-scale fields like medicine, researchers often use 0.01 or 1% to be extra cautious. In exploratory studies, sometimes zero point 0.1 or 10% is acceptable because missing a possible effect is considered worse than false alarm. Step 3. Choose a statistics test. We decide to choose one statistics test based on the problem that we need to solve, based on the business question that we need to solve. T-test answers a question for comparing the group means. Correlation are for a question of are they related? And regression is to predict something like how much does one change when the other changes? Can we predict it? Next, we translate that test statistic into a p-value. The p-value tells us if the null hypothesis were true, how likely would it be to see a result this extreme or even more extreme just by chance. A small p-value means our result would be very unlikely under H0, which is evidence in favor of H1. Finally, making a decision. If p is less than alpha, we reject H0. That means the evidence supports the alternative hypothesis. But if p is greater or equal than alpha, then we fail to reject H0. That means we don't have enough evidence to say something is happening, though it doesn't prove that H0 is true. It just means that we can't rule it out. For better understanding, I have prepared three examples of business questions using the real world data, and we can solve them together using Excel. As you can see, I've collected the data of the amount of HCFC that human has emitted into the air from 1990 to 2021 each year, and the maximum ozone hole each year, which is in the unit of million kilometers square. Our first business question that we need to do some testing is there a significant relationship between the HCFC level and the ozone hole area across years? Let's find out. To answer both questions, are they related? And if one changes, how much does the other change? I might use regression for this example. A regression line of best fit is a linear equation that predicts y, where y represents the ozone hole area in million kilometers square, and it is predicted based on x, which is the HCFC's amount in tons. We need to state both hypotheses before running the test. The null hypothesis says HCFCs do not influence the area of the ozone hole. The alternative hypothesis says HCFCs have a non-zero effect on the ozone hole area. Now we can run the test in Excel. To run the test, you need to choose the table, choose data, go to data analysis, and choose regression. To run the test correctly, we need to specify the dependent variable and independent variable. In this case, the ozone hole area is the one we can predict, which is the dependent variable. If there's enough evidence that the HCFC amount is its predictor, the independent variable. The result shows that p-value equals 0.0396, which is less than 0.05. We come to the decision of rejecting the H0. Conclusion: there's a significant relationship between the HCFC levels and the ozone hole area across the years. We also have the regression model. We have the intercept of 21.00703.161 and a slope of 0.000118743. This means that with every 1 unit change of HCFC level, the ozone area changes about 0.000118743 million kilometers square, which is more than 118 kilometers square. Let's move on to the second business question. Based on the regression model, what is the predicted maximum ozone hole area when HCFC consumption reaches 48,000 tons? So right now, we have the amount of HCFC is 48,000 tons. So we have Xi is 48,000 and Y is the linear regression, the linear equation that we had before. All we need to do is to plug the xi 48,000 in and we have the result. Y equals 26.71. So when the HCFC consumption reaches 48,000 tons, the predicted maximum ozone hole area is 26.71 million kilometers square. We've come to the final business question. The question is there a statistically significant difference in the average minimum ozone hole area between the years of 1990 to 2004 and the years from 2005 to 2021? For this problem, we have two independent groups that needed to be compared with each other. So we will use the two sample t-test to compare them. And we will choose the two sample t-test with an equal variance because we don't know how the distributions look. So an equal variance would be a safer choice unless we know that they're equal. Group 1 is the ozone hole area values before 2005, and the group 2 is the ozone hole area values from 2005 onward. We have the H0 and H1 for the hypothesis. H0 is when the average of two groups are identical, and H1 is when the two groups are different. We're given the p-value of 0.178, which is larger than 0.05, so we fail to reject H0. Conclusion: there's no significant evidence that the ozone hole area value from group 1 is different from the ozone hole area values from group number 2. Isn't it simple? So why? Why do we go through all of this? Bottom of the line, because hypothesis testing gives us a disciplined way to make decisions under uncertainty, whether it's testing a new drug, evaluating a business strategy, or studying environmental changes like ozone depletion. Hypothesis testing helps us decide, is this real effect or could it just be a chance? It doesn't give us absolute truth, but it does give us a structured, transparent way to weigh evidence and manage risk, and that's the real power of hypothesis testing. Thank you so much for listening. I hope you enjoyed the video.